Hi everyone, my name is Laura and today I'm going to present my graduation project presented for the degree of microbiologist, which is named as polymeric microencapsulation of the fungal enzyme lacase through microfluidic system for its potential use as a biocatalyst in wastewater treatment. The current presentation is divided as follows: introduction, objectives, methodology, results and discussion, and conclusions. First, as context, we know that most human activities that use water produce wastewater, and as the overall demand for water grows, the quantity of wastewater produced and its overall pollution load are continuously increasing worldwide. So wastewater treatment has become an important worldwide priority during the past decade because if wastewater is not properly treated, it may negatively impact the environment and human health, thus turning into a costly problem to most governments and countries. Now, conventional wastewater treatment technologies like activated sludge cannot eliminate these pollutants completely, so enzymatic treatment arises as an alternative method for the treatment of organic micropollutants. There are multiple methods of enzymatic immobilization, such as physical absorption, chemical binding, polymer entrapment, and microencapsulation as the most used ones nowadays. Moreover, recent studies have suggested that droplet-based microfluidic systems offer a more controlled reaction environment and the chance to reduce the amount of reagents required for manufacturing, thus providing an inexpensive manufacture process. In this sense, our main objective is to establish the lacase encapsulation efficiency and its enzymatic activity in different pH and temperature conditions in order to determine its potential use as biocatalyst in wastewater treatment. There were 8 major experimental steps in the project. The first step was to perform the microsystem design and manufacture for microcapsules generation and to perform the parameter optimization. Using the parameters found in the previous step, the following step would be the lacase encapsulation and the enzymatic activity upon pH and temperature. Then it was the microreactor design for wastewater treatment and the preliminary test of the encapsulated lacase in the microreactor, which consisted of pumping artificial acetaminophen diluted water through 3 different microreactors set to a pH of 4.5, and 6. Lastly, we characterized the microcapsules before and after the wastewater treatment, and we performed a phytotoxicity test. Results are divided into 5 main steps. The first step of our methodology, the design and manufacture of the microfluidic device, was carried out following the procedure described by Campaña et al. So, a flow-focusing approach was selected to manufacture the polymeric capsules due to the facility it offers to maintain great control over the size of the microcapsules. Also, in the figures, we can see the dimensions and total size of the final microsystem. We tested 4 different combinations of continuous and discrete flow rate values. As we can see in the figure on the left, the optimal flow rate ratio to obtain a size distribution of around 1000 micrometers was 80 over 0.7 milliliters per hour. This in order to avoid loss of microcapsules due to the channel and outlets width of the microreactor. Now for the lacase encapsulation, the same flow rates were set and no significant variation was observed in the size of the lacase encapsulated microspheres generations. Shown in the figure, the activity of the enzyme has a linear behavior within the range of 4 to 8.0 pH. We can see in the graph that as the pH increases, the rate of enzyme activity decreases, and an optimum activity is reached at the pH value of 3.0. And the continued increased pH results in a sharp decrease in activity as the enzyme's activity site changes shape or is denatured. So we argued that an acidic pH is relevant because lacase enzymes oxidate substrates by transferring electrons from the substrate to the copper active sites of the enzyme, and copper relative abundance increases rapidly with a pH lower than 6. On the other hand, the activity evaluation upon temperature showed that as the temperature increases, so does the rate of enzyme activity. However, temperatures higher than 65 Celsius show a sharp decrease in activity because the enzyme becomes denatured and can no longer function. Results show that the substrate is interacting with the microcapsules by adsorption into the surface of the capsules. In this sense, absorbed molecules might leave the surface with the same chemical identity or may suffer a degradation catalyzed by the lacase. Both of these phenomena will lead to an eventual dynamic equilibrium in the microreactor. Therefore, the substrate degradation by the lacase would lead to a decrease in the registered UV-based absorbance at the wavelength of the acetaminophen, as shown in the figure on the left. Now, the figure on the right shows that for a pH value of 6 and 3.0, a greater concentration of acetaminophen was degraded, with a final concentration of about 57.3% of the original concentration, being the final acetaminophen reduction of 42%, 30%, and 72% for the pH values of 3, 4.5, and 6.0. So microreactors set to pH 6 had the best results for the acetaminophen degradation, which make us hypothesize that the entrapping of the enzyme in the alginate framework favors the enzymatic activity, providing an enclosed environment, and that in turn favors the relative concentration of copper in the medium. Now, the encapsulation efficiency was calculated to be 21.6%, and on the other hand, as shown in the figure, although the loss of lacase was found to be 117.26 units per milligram, the enzymatic activity was successfully maintained after the encapsulation process. This encapsulated microsphere exhibited a typical rounded shape morphology and some surface protrusions. These results are similar to the ones reported by Campaña et al. For the microspheres after 20 days of fabrication, which can confirm the stability of microcapsules within 1 to 2 weeks. On the other hand, the EDS analysis shows the presence of carbon, oxygen, aluminum, silicon, and copper as components of the microsphere samples, where the one that shows a greater proportion according to weight is copper, with a percentage of 25.93%, and this is a relevant result since, as it was mentioned before, relative abundance of copper might be relevant for the oxidative capacity of lacase enzymes. For the phytotoxicity test, there was not significant difference in terms of toxicity decrease within microreactors, so we argue that the pH value does not have a significant impact on the toxicity of the solution, but the enzyme activity itself. However, the use of the lacase encapsulated microspheres as filtered for the treatment of wastewater sample clearly reduced the phytotoxicity of the solution, demonstrating not only an acetaminophen removal from the sample, but also a reduction of the toxicity properties of the components making up the outcoming treated water solution. So we can conclude that microsystem design and manufacture was successfully achieved. The optimal parameters for the flow rates were found to be 80 over 0.7 milliliters per hour, and the lacase encapsulated microspheres didn't show significant variation in size compared to the alginate microcapsules and showed to maintain their enzymatic activity after encapsulation process. Lastly, preliminary tests using the microreactors showed an acetaminophen degradation of 42%, 30%, and 72% for the pH values of 3, 4.5, and 6 respectively. So we could deduce that it serves as an efficient wastewater treatment technique. Here I'm showing some references used in this presentation, and thank you so much for the attention.